Okay, so part of the purpose today is to review some things to kind of measure what you're coming into the class with for skills. Some of the topics we cover today, we will go back over at some point during the course and go over them in more detail. But we're going to kind of skim through these today just to see what your level of knowledge is with these topics. So we're going to start out with graphing. Now, of course, we're all familiar with the Cartesian, or the rectangular coordinate system, where you have the x variable on the horizontal axis, the y variable on the vertical axis, and we can plot points on it. You know, -4, 7 means that from the center, the origin, you're going back to -4 on the x-axis, up to +7 on the y-axis, and you're putting a point there that lines up with those two coordinates. I'm not going to spend time on plotting points because we're going to assume that you guys know how to do that. But we are going to look at how do we graph certain types of equations. Y = 1/2 x - 3. Hi. Okay. Okay, thanks.
Okay, thank you.
So y = 1/2 x - 3. There are shortcuts for graphing this, and we will get to those as the course goes on. But for right now, we're going to look at filling in a table and then plotting it point by point. So to graph it, we are going to pick values for x and then use that value for x and our formula to calculate the required value for y. Now, as we graph, we're looking at the basic XY graph here. We want to make sure we get points that are spread out across this graph. So I'm not just going to pick values for y like 1, 2, and 3. I want points that are spread out. Now, I'm also going to make sure I'm smart to pick points that work out well. I know that this is 1/2 times x. So if I pick even numbers for x, it's going to make my calculations a lot easier to do. So I'm going to start out with -4 as my first value for x. If I plug that in for x, I get 1/2 times -4 minus 3. What is 1/2 times -4? -2, thank you. Now -2 minus 3? -5, perfect. So that gives us an ordered pair here, x = -4, y = -5, like that. I'm going to go ahead and fill that in on the graph right now. -4, -5 is right there. My next value that I'm going to use for x, I'm going to use -2. Again, I'm sticking to the even values because it's 1/2 times x, and I'm spreading them out across the graph. So if x is -2, I fill that in. 1/2 times -2 minus 3. Once again, what is 1/2 times -2? -1. And -1 minus 3? There we go. Thank you. I know the cameras can be a little intimidating to speak, but the course goes a lot smoother if you speak up and answer questions. Don't let the cameras scare you. And I promise I won't embarrass anybody for a wrong answer. Class participation makes everything go a lot quicker for everyone. So we've got -2, -4. That is somewhere in here. Let's take a look at what if I have 0 for my value of x. So we have 1/2 times 0 minus 3. What is 1/2 times 0? 0, good. 0 minus 3? It's -3, good. So we have the ordered pair is 0? Perfect, thanks. So the ordered pair is 0, -3. So 0, -3 is right there. Now at this point, you probably have figured out what shape this graph is going to make. Well, let's keep going. Let's put at least one more point in there to be sure. Let's pick 2 for x. So 1/2 times 2 minus 3. What is 1/2 times 2? 1. Perfect. 1 minus 3? -2. So that gives us the ordered pair 2, -2. So +2, -2 is right there. At this point, we're pretty sure that that is just a line across our graph looking something like this. Now, as we're looking at this graph, there are some special features that I want to point out. Now, we know that this is the x-axis of our graph. Where the curve of the graph, or in this case, the line of the graph, crosses that x-axis is called the x-intercept. That's an important point because many of our graphs, it's easy to find, or relatively easy to find, the x-intercept. Of course, we know this vertical axis is the y-axis, and likewise, where the graph crosses the y-axis is referred to as the y-intercept. And again, it's often relatively easy from an equation to find the y-intercept. So if you know the shape that a graph is supposed to be, and I'm certain, imagine many of you can probably look at an equation like y equals 1/2 x minus 3 and possibly remember that that is going to form a line. If not, we're going to go over rules as to why we know that forms a line at some point through the semester. But if you know what shape it has to be and you know those intercepts, that's all you need to know to graph the line. If I had an equation and I was looking for those intercepts, let's look at my x-intercept. I don't necessarily know the value of x there, but I definitely know that being on the x-axis, that the value of y has to be what? 0. Good. Y has to equal 0. So I can take my equation and put 0 in for y. 0 equals 1/2 x minus 3, and I can solve that for x. I would add 3 to both sides to get 3 equals 1/2 x, canceling out that minus 3. And then to get rid of the 1/2, I can either divide by 1/2 or multiply by 2 to get 6 equals x. So that x-intercept is at x equals 6, or it's at the point x equals 6, y equals 0. Any coordinate on a graph, by the way, if it's a point that is on the graph of that equation, if the x or if the y coordinate is 0, it is an x-intercept. So we find the x-intercept where y equals 0. What do we know about the coordinates of the y-intercept? X has to equal 0. It goes through the 0 of the x-axis. So to find that from the equation, we'd put 0 in for x. So y equals 1/2 times 0 minus 3. This one's a lot easier to solve. 1/2 times 0 is 0. 0 minus 3, -3. So that's telling us that at y equals -3, or the point x is 0, y is -3, that is our y-intercept. If we know that this is a line, that's all we need. Any 2 points on the line can define the line. There's no other variations that we could have from those. However, not everything we're going to graph is going to be a line. We can run into things like y equals x squared minus 2x minus 3. So if we want to graph this, let's fill in a table and plot some points. We're going to pick some values for x again. making sure that we spread them out across the graph. So let's pick a value for x. Oh, let's not get too carried away. Let's just do -3 and see what happens. So I'm going to put in -3 wherever the x is. So if x is -3, x squared is -3 squared, minus 2 times -3 minus 3. Word of warning on your calculators, by the way, -3 squared. If I just do -3 and hit x squared, it tells me that it's -9. What should -3 squared be? +9. You got it. It's -3 times -3. We know a negative times a negative is a positive. Well, why did the calculator tell me -9? Well, the calculator does a strict order of operations. It applies the power first, does the squared first, and then applies the negative. So it is saying 3 squared is 9, and then it's applying the negative. To do a negative number squared on almost every calculator, you have to put the negative number in parentheses, and then do the squared or the power of 2 to get 9. So -3 squared is 9. I'm going to treat this as -2 times -3, which is +6, and then perfect, and then -3. So what is 9 plus 6 minus 3? 12, good. So this is -3 comma 12. So -3 is here, 12 is off the top of our graph. So that point isn't horribly useful for us right now. Let's go closer to the center and see what happens. So let's try x equals 0. So 0 squared minus 2 times 0 minus 3. What is 0 squared? 0. 2 times 0? 0. So then all we have is 0 minus 3, which is? -3, good. So that gives us the ordered pair 0, -3. 0, -3 is right there. So that is one useful point on our graph. Well, let's keep going over to the right. Let's try 2, +2, see what happens. So that's going to be 2 squared minus 2 times 2 minus 3. What is 2 squared? 4. Minus, what's 2 times 2? 4. So 4 minus 3 is? -3 again, good. So that gives us the ordered pair 2, -3. So 2, -3 is right there. Is this shape going to be a line? No. No, it's not. It's going to be a parabola, exactly. It's not going to be a line. We know from the form of the equation, it's an x squared. It's a second degree equation. It's what we call quadratic. It's going to form a parabola. So we cannot just get those 2 points and draw a line through them. There's more to it. But from those 2 points, it tells me there's certain things I want to learn. I want to learn what's going on between those 2 points. Well, that would be at x equals what value? 1. So let's try that. Let's do x equals 1. If x equals 1, y will be 1 squared minus 2 times 1 minus 3. What is 1 squared? 1. What's 2 times 1? -2 and minus 3. So 1 minus 2 minus 3 is? -4, giving us the ordered pair 1, -4. Now, some of you might look at this, is that 2 times 1 is 2 and then 1 minus 2? Or is it negative 2 times 1 is negative 2? It can be either way. If I treated that as negative 2 times 1, well, then it's just plus a negative 2, which is the same as 1 minus 2. 1 plus a negative 2 is negative 1. 1 minus 2 is negative 1. So you can work with it either way. So we plot that point. 1, negative 4 is right there. But we want to also know what's going on out here. Now we did negative 3 and that shot off our graph. So what point should we use over here for, what value for x should we use to figure out what's going on over here? Negative 1. Perfect. So let's use negative 1. So we put in negative 1. We've got negative 1 squared minus 2 times negative 1 minus 3. What is negative 1 squared? 1, positive 1. Negative 2 times negative 1? Positive 2. So then we have 1 plus 2 minus 3 is 0. So we got negative 1, 0. Let's plot that point. Negative 1, 0 is right here. That gives us a decent picture of what's going on. What about over here? What value should we use for x to figure out what's going on that side? Let's just go to 3. We've done up to 2. Let's go to 3. See what comes next. So we'll use x equals 3. So y will be 3 squared minus 2 times 3 minus 3. What is 3 squared? 9. 2 times 3? 6. 9 minus 6 minus 3 is 0. Good. So that gives us the ordered pair 3, 0. So that's a point right there. Now you might get that this is symmetrical. So we're going to get a parabola. Oops, get back here. It'll look something like this. Now this is one, again, we still have x-intercepts and y-intercepts. We have 2 x-intercepts here. And we only have 1 y-intercept. Now in this case, they wouldn't necessarily be quite as useful for graphing, but they're relatively easy to find. We actually calculated the y-intercept when we did x equals 0. 0, negative 3 is that x-intercept. Now the y-intercepts we found, but just because we happened to pick the right x values to give us a value of 0 for y, but we could have put in 0 for y and solved that for x when y is 0. Now, of course, that's going to require us to do some factoring. We'll come back and we'll look at that in a little more detail later on today. There are some other kinds of equations we might want to graph. One might look like this. Y equals 2 to the power of x. Another one might look like this. Y equals 2 times the absolute value of x minus 3 plus 1. Remember this symbols here, these vertical lines are absolute value symbols. Or we might have y equals 8 over x. It is 10:20. Normally I like to take a break somewhere in the middle of class here. So let's do about 8 or 9 minutes here. We'll start talking again at 10:30. During break, if you want something to do, you can try to graph each of those 3 equations. We will take a quick peek, we'll go through them very quickly when we come back from break. Did anybody take some time and graph any of these while we were out? Okay, well, let's take a look then and see what we can figure out maybe not going to totally graph them, but let's see what we can figure out with it. From this first one here, if I wanted to find the x-intercept, if I put 0 in for y, 2 to what power could give me 0? Well, there is no power, no number I can put in for x, so that 2 to the power of x is 0. Technically, it'd be the limit as x goes to a negative infinity. Well, it can't ever reach that value. So there is no x-intercept for this. So if I'm graphing this equation, I know that it is never going to cross this x-axis. Let's find a y-intercept. And the y-intercept, to be fair, is generally easier to find. We put 0 in for x. Y equals 2 to the power of 0. Well, that just equals 1. Anything to the power of 0 is 1. So the point 0, 1 is the y-intercept. If we were to plot points, we would find that graph to look something like that. In this case, the x-axis here is something called an asymptote. And what an asymptote means is the graph approaches that line, but it never crosses it. So this graph approaches the x-axis, but it will never touch or cross that x-axis. In other words, the value of y will never be 0. For the second one here, let's do the y-intercept first by making x equals 0. Well, 0 minus 3 is negative 3. But the absolute value of negative 3 is a positive 3. So y equals 2 times 3 plus 1, which is 7. So that's going to have a y-intercept of 7, and only 1. So that y-intercept is right there at the point 0, 7. Our x-intercept might be a little trickier to find. We have to let y equal 0. So 0 equals 2 times absolute value of x minus 3 plus 1. So we have to do a little work to isolate the absolute value to solve this. We subtract the 1. Negative 1 equals 2 times the absolute value of x minus 3. We would divide by 2 here. So we've got negative 1 divided by 2 is negative 1/2 equals the absolute value of x minus 3. Now there's an issue here. An absolute value can never be negative. So the absolute value of x minus 3 can never equal a negative 1/2. What that's telling me is there is no x-intercept here. It does not cross the x-axis, just like the first example. In fact, this one will look something like this. It's a V-shaped. If we plotted points, we could find that. Y equals 8 over x actually has 2 asymptotes. If I put 0 in for y, there's nothing I can divide 8 by to get 0. If I put 0 in for x, well, I can't do 8 divided by 0. We're not allowed to divide by 0. So for that graph, both the x and y axes are asymptotes. That graph can't cross either one. It does not have either an x intercept or a y-intercept. It actually ends up being a graph looking something like this. So I made a big deal about the x and y intercepts when we graph the line and the parabola. And they are important, but you can see they don't always tell the whole story. They give some of the information, but in equations like this one, there are no x and y intercepts. They don't always give us a lot of information about the graph. So we did some work solving linear equations up there. Let's take some time to look at linear equations and solving them, and just to cement the steps involved. Let's actually do this. I actually want to start out with something like this. All of our linear equations, of course, the big thing about a linear equation is we know it has no powers on the variables. All the variables have a power of 1. But anyway, all of our linear equations start out as simple as this, as a variable equals a number, and they are built up from there. We can think of this symbol, the equal sign, as indicating a balanced scale. What's on one side has exactly the same value as what's on the other side. So as we build onto these equations, we have to keep that scale balanced. So if I want to add a 4 to the x to make that x plus 4, I have to balance the scale by adding 4 to the other side to make that 11. When we are asked to solve an equation, what we're being asked to do is to take the equation apart and get it back to that original form. This one was built by adding 11. We take it apart, by adding 4. We take it apart by subtracting 4. That removes the plus 4 there to make that x. And to keep the scale balanced, we subtract 4 from the other side to get that to a 7. X equals 7, which is exactly where that started. Now in this case, I picked that 4 to build onto the equation, so I knew how to take it apart. The tough part is looking at an equation and figuring out how it was built, and then from there figuring out how we need to take it apart. So if I have an equation like 3x minus 7 equals 26, to figure out how it was built, I first locate the equal sign, which is right there. Then I identify the side that has the variable. That's this side over here. And then we ask, what is keeping the variable from being by itself on that side of the equation? Well, we have the 3 and the 7. Then we also ask what operations are attaching those numbers to the variable. The 3 is multiplied, the 7 is subtracted. So now we resort back to our order of operations to figure out what has been done to the variable and in what order. So the variable, we've had the 7 is subtracted, the 3 is multiplied. According to order of operations, we multiply before we subtract. So when this equation was built, the value, whatever value you put in for x would be multiplied by 3 first, and then it would have 7 subtracted from it. Now, if you think about putting together a model or putting together a piece of furniture, if you've just finished, you've just put on that last piece, and you need to take it apart. The first piece you're going to have to take off is going to be the last piece you put on. Perfect. The last piece you put on. So when we take these apart, it's the same way. The last piece we put on was subtracting 7. That's the first piece we take off. And how do we take it off? Add 7. So we add 7, removes the subtracting 7, leaving us with just the 3x. But again, we have to worry about balancing that scale. So we have to add 7 to the other side. 26 plus 7 is 33. Now the only piece we have to get rid of is multiplying by 3, and we get rid of that by dividing by 3. And again, we balance the scale by doing exactly the same thing to both sides. So that 3 is gone. We have x here equals 33 divided by 3 is 11. Perfect. Now, if you're not sure of your answer at this point, you can always go back to the equation, put in that number for the variable, and make sure it works. 3x, or 3 times x, can be turned into 3 times 11. Does 3 times 11 minus 7, does that equal 26? Well, order of operations says we do 3 times 11 first, that's 33. Then we subtract 7, that's 26. So yes, that is a valid equation. We have the same value on each side. Now, I'm not going to insult you by doing a lot of examples like that because I'm going to assume that you guys have solved on your equations. We're going to look at more complex ones. So we have something like 7x minus 9 minus 5x equals 3x plus 7 minus 5x. So looking at this, we find the equal sign, and we try to identify where the variable is, but unfortunately, the variable is on each side. When we solve an equation, there's often steps we have to take before we can solve. The first step that we look for is trying to combine anything we can on each side. In this equation, we can combine on the left side 7x, and we have to remember this is not a 5x, it's a negative 5x. The symbol in front of it goes with the term that comes after it. So what is 7x and negative 5x? 2x. Remember, we still have the minus 9 there, the negative 9. That's all we can combine on the left side. What can we combine on the right side? (3x) and negative 5x. What's that going to give us? Negative 2x. And again, we got to remember we have the plus 7 there. So we've combined everything that we can on each side. The next thing we need to do is we need to make sure that we have the variable on only one side. Here, there's a variable on each side. So we're going to have to get rid of one of them. Generally, it's simpler. We avoid working with negatives if we get rid of the smaller one. Which one is smaller here? Negative 2 is smaller than positive 2, right? So we're going to get rid of the negative 2x. Since it is negative, we get rid of it by adding. If it were positive, we'd get rid of it by subtracting. So we add 2x, makes that go away. It leaves us with 7 on the right side. We have to add 2x to the left side as well. We can only combine it with other x's. So I'm going to add 2x to the other 2x to get 4x, remembering that we have the minus 9. Now that we are in this form, we can do the third step, which is to solve. And remember, solve means we take it apart. So what's the first piece we're going to take off of this? We're going to add 9 to get rid of the minus 9. Perfect. That'll give us 4x equals 16. And then divide everything by 4. X equals 4. Perfect. Any questions there? And of course, we can get bigger than, or we can add in other complications like parentheses. something like this. Now there's a couple of things here that are a little bit tricky to deal with. Now remember, the first thing we want to do is combine on each side. So here's the equal sign. I'm going to work strictly on the left side first, combining everything I can. Whenever we see parentheses, we have to ask two questions. Is there anything that needs to be done inside the parentheses? So for that one, can I combine the 3x minus 2? No, I can't. Second question, is there anything that needs to be done to the parentheses? And in this case, it's multiplied by 5. So we're going to have to distribute. 5 times 3x is 15x. And 5 times negative 2?
Negative 10.
Negative 10. Good. The second one here, is there anything that needs to be done inside that parentheses? No. It is also being multiplied, but it's not being multiplied by 3. It's being multiplied by negative 3. Good. Negative 3 times 4x? Negative 12x. Good. And negative 3 times 1? Negative 3. Now we can still combine on this left side. 15x and negative 12x make 3x. Good. Negative 10 and negative 3? Negative 13. Perfect. Now we can go to the right side. There's nothing more to combine on the left. First set of parentheses, we're going to do what? Distribute the 2. 2 times 7x? 14x. 2 times negative 5? Negative 10. Good. The second parentheses, nothing to do inside of it. Yep. There you go. That's okay. A lot of times we've taught to distribute the negative. What we're actually doing is distributing a negative 1. But works the same way. Negative 1 times 11x? Negative 11x. Good. Negative 1 times 4? Negative 4. And we can combine there to get what?
3x minus 14.
Perfect. 3x minus 14. So we have combined everything we can on each side. Next step is to get the variable to one side. It's on both sides right now. The problem is we go to get rid of it. I'll subtract 3x here. If I subtract 3x here, it disappears on both sides, leaving me with negative 13 on the left and negative 14 on the right. Is this true?
No.
No. There is no value of x that I can put into an equation like this to make negative 13 equal to negative 14. This is what we call an inconsistent equation. It has no solution. Now, there are several cases where the variables in an equation might disappear. We might have an equation like this. This is a relatively simple equation, but I want to show you what happens when the variables go away in this case. So on the left side, there's nothing to combine. On the right side, we can combine what?
3x plus 4x equals 7x.
Perfect. 3x and 4x will give us the 7x plus 2. Now we go to get the variable to one side. Again, when we subtract the 7x, it disappears. But in this case, we have 2 equals 2. Is that true? That is true. This is what is referred to as an identity. Is there any value I can put in here for x to make this not true? No. So in this case, the solutions here, I can put any real number in for x, and it'll be a solution to this equation. Because this equation is an identity. The left side and the right side are identical no matter what value I put in for x. Well, let's move on to a somewhat more complicated equation. Something like this. X plus 2 over 7 minus x minus 5 over 4 equals 2. When we have equations like this with fractions in them, we have a few options. We can work with the fractions, or we can get rid of them. In this case, getting rid of the fractions is probably the way to go. I look at my denominators. In this equation, I have denominators of 7 and 4. For 7 and 4, what is my least common multiple, or my least common denominator? If I were adding 1/7, there we go. If I were adding 1/7 and 1/4, I would have 28 would be my common denominator. So that's my least common denominator, my least common multiple for 7 and 4. So what I'm going to do is I'm going to multiply this whole equation by 28. So I have 28 times the x plus 2 over 7. So I'm going to make this 28 over 1. The x plus 2 over 7, I'm going to put parentheses around that numerator just to make it clear how we're handling this. Now I can cross cancel here. Because that 28 is a common denominator, we should be able to cancel with each denominator. 28 and 7 both divide by 7 to give me 1 and 4. So my denominators are gone. My denominator is 1. And I just have 4 times the x plus 2. So I'll distribute that. 4 times x is 4x. 4 times 2 is a positive 8. The next part here is a little bit trickier. I have 28 times this piece. Now that's a negative over times the x minus 5 over 4. So I've got the x minus 5 over 4. Now I'm going to put parentheses around the x minus 5. But there's a negative 1 multiplying that. And then that is multiplied by the 28. So what I'm going to do is this. I'm going to put the negative 1 over 1 for now. But I'm going to cross cancel the 28 and the 4. Both divide by 4. It'll give me a 1 and a 7. Now when I multiply here, I am going to multiply the 7 times the negative 1 to get a negative 7. And then I'm going to distribute that. Negative 7 times x, negative 7x. Negative 7 times negative 5 is a positive 35. Good. Now we're at the equal sign. This part's the easy part. 28 times 2 is 56. Good. Now this is reduced to an equation that we know how to solve. What am I going to do here to solve this equation now? Perfect. We're going to combine what we can. The common variables are like terms. 4x and negative 7x make? Negative 3x. Good. 8 and 35?
Positive 43.
Positive 43. Good. Equals 56. Now to take it apart, what do we do? Where do we start?
Subtract the 43.
Subtract the 43. Good. That's gone. We've got negative 3x equals 13. And then? Divide by the negative 3. So x equals a negative 13 over 3, or a negative 4 1/3. What do you think? Loads of fun? Not yet? To me it is. So we might run into something like this. As we go to solve something like this, There is only one denominator here. That only denominator is the x minus 7. So we are going to get rid of the fractions by multiplying this by x minus 7. The first part here is pretty easy. X minus 7 times x over x minus 7. Well, the x minus 7 just cancels out. That's x. Times the negative 5 over x minus 7. Again, the x minus 7 cancels out. That's negative 5. Equals x minus 7 times 3. Perfect. We have to distribute the 3, giving us 3x minus 21. Now what do we do? Perfect. We got x on each side. The smaller one's the x. Sorry, I didn't mean to cut you off there. So we subtract x. So we've got a negative 5 here. 3x minus x is 2x. We have negative 21. So now the variable's on one side, so we're ready to go ahead and solve. What's our first step? Add 21 to both sides. Negative 5 plus 21 is 16. Good. 16 equals 2x. We're going to divide by 2 to get 8 equals x. Good. Now again, if you were unsure, you could go back up here and put 8 in wherever there's an x and see what happens. This would be 8 over 1, which is 8, minus 5 over 1, which is 5, and that does equal 3. Well, they can get a little worse than that. We can run into equations like this. I have to write smaller here. Kind of backed myself in a corner there by writing too big to begin with, but you guys get the picture. Once again, here's our equal sign. So we're going to combine everything we can on the left side. Now the multiple parentheses, just like with order of operations, we're going to work left to right. So this is the first one. There's its other end. So we're going to start inside that brown box. But we still have to follow order of operations. Inside there, there's another set of parentheses. So we narrow down to that set of parentheses. Is there anything we can do inside that set of parentheses? No. So we're going to distribute the negative 4. So negative 4 times x? Negative 4x. So negative 4 times 7?
Negative 28.
Negative 28. So we still have that. Now, before we distribute this negative in front of that parentheses, let's combine what we can inside here. We have 4 and negative 28 makes? Perfect. Negative 2x and negative 4x makes? Negative 6x. Good. Now we have that negative out front that we should distribute. Remember, treat that as a negative 1. Negative 1 times negative 24 is 24. Negative 1 times negative 6x? 6x. Now this is a positive 24, so I'm going to put plus in front of it so I can bring down the 45. Only one thing left to combine here, and that is 45 and 24 make? So we got 69. So 69 plus 6x is my left side. On the right side, we have multiple parentheses there. Going left to right, here's our first one. Nothing to do inside of it, so we are going to distribute the -4. -4 times 1 is -4. -4 times 3x. -12x. Perfect. Now, while I'm here, we have this set of parentheses. We have to work inside there. We're going to narrow down to this inner set here. I'll change colors. That green one, there's nothing to do inside there, so I'm going to distribute the -3. -3 times x is -3x. -3 times 2? -6. Good. Now then we have this next set of parentheses here. We're going to distribute the -2 through there. -2 times 2x, -4x, and -2 times -5, +10. Now there's still a parentheses there, but before I do anything with it, I am going to try to combine. What can I combine inside here? 4, -6, and 10 make 8, good. -3x and -4x make -7x. Perfect. Now we want to distribute the -1. So I have -1 times 8 makes -8. -1 times -7x, +7x. We bring down the -4 and the -12x. Now, of course, we can do some combining here. -4 and -8 make -12. -12x and +7x make -5x. Good. Okay, so now we've combined everything we can on each side. That was a chore in itself. But we still need to get the variable to one side. Which variable am I going to get rid of? -5x. It's negative, so I'm going to add it to get rid of it. Adding 5x to the other side. So this will be 69 plus 11x equals a -12. Now we can solve. What are we going to do? Subtract 69, giving us 11x equals -81. And then divide by 11. X equals -81 over 11, or -7 and 4/11, or -7.363636. At this point, my math lab should specify what form it wants the answer in. If you give the answer like this, and it says the correct answer should be the improper fraction, if it's a homework, don't worry about it. But if it's a quiz, the quizzes are graded for accuracy. Let me know, and I'll make sure I change those grades for you. Not all of our equations are linear. This is the quadratic equation. When we graphed it, remember we said it formed a parabola. To solve a quadratic equation, we actually saw one of these up above looking for the x-intercepts. To solve a quadratic equation, we need a little bit different strategy. We can't just get the variable, get the x by itself. Now this one is y equals x squared minus 3x plus 2. Up above, we were looking for x-intercepts, and x-intercepts occur where y equals 0. Now this is a different equation than I used up above, but I'm still doing the same process, trying to find the x-intercept. In fact, to solve a quadratic equation, we need to get the whole thing with 0 on one side of the equation. So putting 0 in for y is kind of the first step in the process anyway. So now to solve this, usually there's two possible values for x. We're going to have to factor. Now remember, factoring, there are several processes. The first process you would always try to use is the GCF, greatest common factor. Well, there isn't any common factors in those digits, in those terms of that equation. The second, if it's a 3-term, you would attempt to do reverse multiplication. If you were taught FOIL, many of you were taught this as FOIL in reverse. If it's 4 terms, we use grouping to try to factor it. Well, this one here has 3 terms. So we're going to try to factor it using that reverse multiplication. So we're going to try to break a 3-term or a trinomial down into two-term pieces or 2 binomials. And if you recall from your factoring before, these first 2 terms, the first 2 digits, have to multiply to make this first term of the trinomial. Well, the only 2 things that multiply to make x squared, I mean, we could do 1 times x squared, but that doesn't make much sense. It would have to be x times x. These last 2 digits have to multiply to make the last digit of the trinomial. Well, to multiply to make 2, it's 1 times 2 or 2 times 1. The only other option would be to be -1 times -2. Now, in this case, which one is it going to be?
-1 and -2.
How'd you know that?
Because the middle number is negative.
Because that's a -3x in there. That means we're going to have some negative components. Very good. So we're going to do -1 and -2. Now, to make sure that that is what we want, let's double check it. Let's do that FOIL. Well, the x times x is x squared. We knew, oops, I put in a 1 here. That should be a 2. We knew that that was going to work. It's this outside and inside that really is going to determine whether this works. X times -2 is -2x. The inside -1 times x is -1x. Then the L, the last, -1 times -2 is a +2. Notice these digits worked. There was no question those digits were going to work. It was whether these middle 2 were going to combine to make the -3x, and they do. -2x and -1x does make -3x. So that is the proper factoring for that expression. Well, the reason we got to this is because now we're going to use that to find the solutions for this equation. Those 2 multiply to make 0. And our 0 product rule tells us if 2 things multiply to make 0, then either A equals 0 or B equals 0, or both. They can both equal 0 at the same time. So either x minus 1 equals 0 or x minus 2 equals 0. So we can solve this one by adding 1. That's saying x equals 1. Or we can solve this one by adding 2, which says x equals 2. So what that's telling us is if we graphed this parabola, there would be x-intercepts at 1, 0, and 2, 0. Those would be my x-intercepts. If we did a y-intercept, we put 0 in up here for x. If I put 0 in there for x in each spot, what's y equal? 2. 0 squared minus 3 times 0 plus 2 is 2. So y would equal 2. So the y-intercept is going to be at 0, 2. Right there. Now again, that may not be enough information to totally graph the parabola, but it gets us a decent start. Now, one of the other big skills, I know we're running a little short on time, is we want to be able to solve word problems. If we can't put the math into application, it doesn't do us a lot of good to have it. And one of the classic word problems we use is a mixture problem. Very common in chemistry and investing, depending on which route you want to take. Let's look at a chemistry type problem. Let's say that we have a 13% and 25% solutions. And we want, well, let's go with 1,200 milliliters of 16% solution. We want to know how much 13% and 15% solutions should we mix together. So how much to mix? So in an equation like this, we're looking at a total amount, two amounts that have to add up to the total. Our equations can only take three forms. Either we have A plus B equals a total, A minus B equals a difference, or A equals B. If two things add up to a total, they subtract to make a known difference, or they're equal to each other. In this case, they add up to make a certain total. So we have the 13% solution that we are going to be combining with the 25% solution to try to create a 16% solution. The amount of active ingredient in a solution is the concentration, the percent, times the amount. Well, the only amount we know here is the 25 milliliters, or sorry, the 1,200 milliliters of the 16% solution. So I need to know how much of the other two that I'm going to use. Well, I can't use two variables, x and y. That would make this a system of equations. We need to do this with a single variable. So I'm going to let the amount of the 25% solution be x. The amount of the 13% solution will be 1,200 minus x. Because if our total is 1,200, if we use x for the 25%, the total minus x gives us the amount of the other solution. So now we solve. Our active ingredient, remember, is the percent times the volume or the amount. 13%, we're going to write it as 0.13 times that amount of 1,200 minus x. For the second ingredient, the 25%, we're going to add that. That's 0.25 times the amount of x. For our final result, we got 16%, 0.16 times the amount of 1,200. So let's do some combining here. On the left side, I have to distribute. 0.13 times 1,200 gives us 156. 0.13 times negative x, negative 0.13x. and we still have the 0.25x. So we're going to still combine the x's here. Negative 0.13 and a positive 0.25 is a positive 0.12x. On the right side, 0.16 times 1200 is going to give us 192. And now it's a matter of solving this. We subtract 156 from each side, giving us 12x equals, was that 36? Or sorry, not 12, 0.12x equals 36. And then we divide by 0.12. X equals 360 milliliters. Now we have to make sure we go back and answer the question. X, first of all, represented the amount of the 25%. That's 360 milliliters. So we identified what X tells us. The question asks how much 13% and how much 15%. Well, we have the 15%. That should have been 25%. I'm sorry. How much 13% and how much 25%? We have the 25%. That's the 360 milliliters. The 13% is going to be found from this formula. Its amount was 1200 minus X. So 1200 minus 360 is going to give us 840 milliliters. Any questions? I did that wrong, didn't I? That's not 360, that's 300, isn't it? Okay. So this would be 300 milliliters, and this would be 900. Sorry about that. The internal calculator is not quite up to speed for the semester. Okay, we've got 2 minutes left. Anybody have any questions? Okay, so things you need to have done. Very soon, you need to make sure you are registered in My Math Lab. And then, of course, for next week, homework 1A. Like I said, it should be done for class on Monday. It's technically the cutoff date is on Tuesday. I give you that extra day so you can ask questions in class and then have a day to finish it up if you need to. Okay, with that, well, that's our first class. So hopefully it wasn't too boring of a way to start off the semester. We'll see you all next week.